All right. So getting information from graphs. And so this is a lot of what you're going to do in calculus. You're going to find where functions increasing and decreasing, where min and max values are. And how are you going to do it in calculus? You're going to take a derivative. If the derivative is positive, the function's increasing. If the derivative is negative, the function's decreasing. If the derivative is zero or non-existent, we call that a critical point, and that means there's probably, not guaranteed, but probably a local min or max. So what I'm going to teach you today is how to do it all from the graph. So we're just going to show you how to look at the graph stuff, to look at it graphically, so out, um, you can check out if you did your calculus for it later just by graphing and looking at it. So let's do this. So here, if I have a function that is increasing, it may go up, it goes that, and that. It doesn't have to always increase at the same rate, but notice here, here's a real fancy math definition. That means is x goes as the value of x increases, the function value increases. And we say it's increasing if x that. And this is for all such x. So here, if I call this x1, and here I call this x2, here my f of x1 will be less than my f of x2. Okay, put that in parentheses. Okay. So basically all it means is as my function goes up, it goes up. Here, we're going to do the exact opposite here. I'm going to have x1 and we're going to have x2. And then here we're going to have a function that's decreasing. And so here, f of x1 in this case is greater than my f of x. No, my f of x2 is here. Okay. So this will be my f of x2. So this is what it means to be increasing, decreasing. Nothing horribly special. All right. Notice that the rate of increase does not need to be the same. And it just needs to be constant. If you get into higher level math, you'll have a monotonic increasing function and a monotonic decreasing function. That means it can increase and then kind of flatten out and then increase again. It just means it's not decreasing. It's kind of a strange way of saying it. You'll get to that if you get into high level analysis courses, but I don't think as engineers, most of you probably won't take such courses. And the reason is you only have finite time, right? I'd love to learn how to play guitar and piano, right? I also want to learn how to draw. My desire to learn how to draw is so much stronger than play guitar that I spend time doing it. Spend time drawing, then playing guitar. So realize you have a finite life and you need to put finite amount of activities into it. So choose the better and best part, right? Um, Even if you're a religious person, I think you have an infinite lifespan, which some religion people do. Um, your time on Earth's only finite. So for now, we may do other stuff. Yeah, I'll show some of my drawings at the end of class. I'm not very good. All right, so let's do. Oops, let me do this one. Let me redraw this. Hold on, I want to do this in a very particular. There we go. I want to do this. Ta-da! All right, so here, a local min or max is if I have some interval around it that for the minimum, it means, let's do these. Let's do this. So we're going to say the minimums. So here we have a local min here and a local min here. So these are local mins. Okay. So these are local mins. And then we'll have some local maxes. Let's do these max here and here. These are local maxes. And so what has to happen is it only needs to be the highest point in some small interval. And it doesn't matter how small that interval is. In fact, let me draw something right here. Draw technically this over here is also a local maximum, even though like 2 seconds later it's already higher than this. And so here, it doesn't matter just as long as some small interval is the highest point or equal to the highest point. Technically, to be technical, according to these rules, right, if I have a straight line, every point on the straight line is a local min or max because it is less than or equal to everything next to it. And I guess that makes sense. These are different from global mins or maxes. These are different. I'm gonna write that different than global. A global min or max is where a function is at the highest or lowest value. This function here, if it continues to go down forever, which we don't know because I haven't drawn it, would have no global max or infinite, or you might write infinite depending on what you're trying, or negative infinity might be its global min, and then no global max goes up in front of the infinity. All right, so I'll leave you to write that. I'll get to the next page. All right, so let's do this. All right, so here I'm going to give you the functions. And the reason I give you the functions is, notice that a function can have, notice here a function can have if I have a polynomial x at the end plus dot, 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 it can have at most n minus 1 terms in it, okay? And what that means is you can go up and down. So here, this is x cubed. It can have at most 2 terms, which it does have, right? Here I have x to the 4th. It has at most 1, 2, 3 terms, which this case does have. Remember, x to the 4th may have no terms if I just draw it in, if I didn't have these other terms. So it can have less than that. It can have more than that, but it can have less than that, but it cannot have more than that, okay? And so here, when I draw this in, I can strictly say this function is always increasing and always increasing as I go further negative. I can only rephrase that. Always decreasing as I'm coming in, because increasing and decreasing always looks at going in the positive x direction. So, and then here it's always decreasing as I go further. So here, let's go ahead and do that. And so how would I identify these points if I were just looking at the graph? And so we're not going to be 100% precise, right? We're not going to be precise. That's what calculus is for. We're going to be rough here. And so here, I'm going to roughly say this is 1, 2, 3, and a little bit over. I'm going to roughly say this is 3.2, and then I'm a little over 6, so 6.2. So roughly like this. And then here, I'm going to say this is roughly minus 3.2 minus 6.2. Okay. So these, because it is symmetric. All right, so now I want to identify the intervals where it's increasing and identify the local min and maxes where it occurs. All right, I think your homework wants your min and max as points, right? So it's a minimum, a local min point and a local maximum point, which makes a lot of sense. So I think I'm going to give it to you in this case as points. If the homework asks for something different, just ask me tomorrow and we'll fix it. All right, so where's this increasing? Well, this is increasing between the interval of negative 3.2 to 3.2. And so notice the interval is always x values. So here, this is an x value. This is an x value, right? So it's increasing from when x is from here to here. So the interval of increasing is, let me be very clear, the intervals are given in x. right? And so these, so this is, let me write this on the notes, given in x, right? So given in x, so these are x values. So the function's increasing when from x equals to negative 3.2 to 3.2. We do not say, we always put parentheses on this because we do not include the min or max point. Because the max point is neither increasing or decreasing, because here if I look at it this way, it looks like it's an increasing, but here if I look at this way, it looks decreasing, so we say neither. And this function is decreasing on the following intervals. And from here, it goes from negative infinity to the negative 3.2. So it's always decreasing going up to here, because I know this can have at most 2 terms in it. So it's always going to be decreasing until I get to here. And then from here onward, it's always going to be decreasing. So from 3.2 to infinity. All right. So here, I've written it this way as a list of increasing and decreasing intervals. I think your book, just for the sake of homework, and so I'll write it that way. They're going to want a union here. So this in union, this is everywhere the function's decreasing. I like to write it as a list, but I think your homework wants it this way, so I'll put it this way for now. Where's our local max? So our local max here, local max. Our local max is here at 3 and 6.2. Another way of saying this is I have a local maximum at x equals 3.2 with the value of 6.2. Okay. What's my local min? Right here, it's minus 3.2 minus 6.2. Okay. Now, what would you do in calculus? Just real quick, you take the derivative of this, and so I'd have minus 0.3x squared plus 3, set that equal to 0, and then solve for these 2 points. And then here, and then from here, you can also just, at that point, you just use the graph. So these are estimates. This is an estimate. I'm just looking at the graph. That's a terrible way of spelling. I'll just put APPROX approximation. Okay, so these are approximations. We're not going to do it precisely as you would in calculus. Okay, but it's good to know the guesses. That way, when you do it with calculus, you can easily just look at a graph and it's like, okay, I didn't do too bad, right? All right, let's put some points in here. Let's say that's my maximum point. I'm just guessing. So 0, 1. Here, I'm going to say that's a little bit past that. We'll put it right here. We'll put it at, let's just say 7.5 and minus 6. Say it actually occurs at that. And then here, let's just say, oh, let's put it right here. Let's put it right here at minus 3.5 and 0. Okay, so let's just, here you're just going to put points. When I give you a review sheet, you're going to have to do this this in the homework. They have a little thing to help you to get more precision according to what they want. So here, what do we have? So let's look at this. So let's look at the intervals of increasing. So increasing and decreasing. So here we have minus 4 to 0. Oops, not minus 4. Minus 3.5. So from here to here, it's increasing. So here to here. So that's from negative 3.5 to 0. So always look at the x values. Even though that looks like our point, just look at the x. So from here, it's increasing, and then from here to infinity, it's increasing. And I'll go ahead and write it the way your book's probably going to want it. There we go. And then where's it decreasing? From minus infinity up to here. So minus infinity to negative 3.5. And from 0 to 7.5. All right, so we have a local max. So our local max here is 0 and 1. Our local min here is, we have two of them. We have 3.5 and 0 and 7.5 and -6. And notice how this one's a lot more negative or smaller or lower than that one, but this one still counts as a local min because around it is the smallest value. Okay. All right, so there's that. I'll let you copy that down. All right, let's look at this. All right, so let's look at some real world data real quick. So this is from Wolfram Alpha. No one's shocked that I stole it from there, right? So this is the graph, the following of temperatures in Las Vegas in 2019. So 2 years ago now. And this is around when I taught it, right? So this was recent data when I taught it, when I pulled it. I taught this in, yeah, and so here's just the graph for temperatures. So this is what Las Vegas looks like in June. Now, is this what our graph looks like? No. Have we gotten a lot higher than 100 recently? Yeah. It's because we had a heat wave. Today it's not supposed to get so bad. It's only supposed to, I don't know, what was the high today? High supposed to be like 93 today. So it's not supposed to be bad at all. Okay, so let's look at this. So here, find the interval of increasing and decreasing and give the local maximums. What do these values represent? So let's do this. So let's just do some local min points. I don't think we're going to fill this all out. I just don't. There's no reason to. But let's label them all up here at least. And then I'll write out a couple. Okay. So let's say that's a local min. This is definitely a local min. That's real nice and clear. Here we'll go ahead and say that's a local min again. And then here, exactly as I want to show, here we have a local min, right? And so these are our local mins. So how would I write this as a point? Well, here I'd go June 27 at 5:30 a.m. and then I'd write in my temperature. So if this is, so each of these is 5, so this would be about 77, roughly 76. Let's just say 77. Okay. Here, my next one would be June 28th at 6 a.m. And that's a little less than that, so we'll just say that's 74 degrees. Right. Here at June 29th at 6 a.m. Here we have 75 degrees roughly. And then we still have this weird local minimum here. So this is June 29th at, let's say that's 11, 12? We'll say it's 12 p.m. And that's, this is 90, that'll be about 92, 3? I should say 92. Okay. And then here we can put in maxes. Here, 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 and here. I'm just going to write local max. I'm going to write the first one. And then here we can say at June 27. Say that's about 5 p.m. And that was 97 degrees roughly. And then I'm just going to draw dots down. You get the idea, right? And here you could easily determine where's the min and max. You get the idea. We don't need to finish it, right? So let me ask a question real quick. What happened here? Because if you look at this graph, you say, well, the coolest time of the day is about 6 o'clock, 6 a.m., right? Roughly. And the hottest time of the day is about 5 p.m., roughly. So does anyone know what happened here? Anyone have a guess? Were you guys living in Las Vegas on June 29th, 2019? It got cloudy, it rained. And that is the correct answer. It did get cloudy and then it rained, right? And so rain came down, and as rain evaporates, since the evaporation will, since it still needs all that temperature to evaporate, it still needs 112 degrees worth of energy to evaporate, or 212 degrees Fahrenheit to evaporate. But when it evaporates, it just steals that energy from whatever it's on, right? So that's why you get, if you go outside, you get soaked with water, and then it all evaporates off. You get cool because you're not 100, you're not 112 degrees, 212 degrees. If you were, you would not be alive. But that energy still can be, temperature is an average, right? Say the temperature of this room is, I don't know, say it's like 75 degrees because I'm in AC, right? One molecule could have like a really high kinetic energy, and then one molecule could have a really low kinetic energy. And then they'll hit each other, and then one will have high and one have low. So it's just an average amount of kinetic energy. And so when water evaporates, the things with high amount of kinetic energy are just left, and it's just leaving things with lower kinetic energy. And so still some of your molecules kinetic energy as it disappears and evaporates. And so that's kind of how it works. And it was a long time before physicists figured that out, because it's like, what's temperature, right? And so there was like these weird experiments where they'd fill bathtubs full of boiling water to see if they can distill if there is some sort of essence of temperature. It was really interesting how they figured out temperature is just more or less as a collective amount of kinetic energy of particles. So that was all interesting. Anyways, so yeah, it rained. And so here, but still for this graph, what I really want to get into, this is a local min, this is a local max, or this is local max, this is a local min, even though it's very, very small. And so those still count. And so, all right, so that's it for today's note.